So we've been talking about using the fundamental theorem of calculus, which would allow us to work out, say, the signed area underneath some curve, not by using Riemann sums, but by taking an antiderivative, and then evaluating that antiderivative from the lower limit to the upper limit. So on an example like this, we would find any antiderivative, x squared plus 3x, plus possibly any constant, and then evaluate that from 1 to 3. So we would plug in the top value, 3 squared is 9, plus 3 times 3 is 9, plus a constant. Take away the bottom value, 1 plus 3, plus a constant, and then simplify this. 18 plus c, take away 4 minus c, would come out to being 14. Now, if we had something more complicated, like this, for example, we would have to go and work a little bit more carefully. Say we wanted to go and integrate this from 0 to the cube root of pi. Now, according to the fundamental theorem of calculus, since this is a continuous function, we'd have to dig up only an antiderivative of x squared times the cosine of x cubed dx, and then evaluate that from 0 to the cube root of pi. But the key part, the key difficulty, will be in finding an antiderivative for this. Since it's a product, we can't just go and integrate the x squared and the cosine of x cubed pieces separately. First off, I'm not allowed to do that from a calculus point of view, but even then, since I can integrate x squared to 1/3 x cubed, that's not going to help me with this at all, because what would that be? Right? It's not the sine of x cubed, because the chain rule says that that's not going to work. It's also not the sine of 1/4 x to the 4th, because that doesn't even make sense with the chain rule. So what exactly would you do on something like this? Well, let's think about this a little bit more carefully. One of the ways that we might end up with something like cosine of x squared, cosine of x cubed, is that we might have gotten this from the chain rule. Now, the chain rule would say we would have some kind of cosine of blank term, and then this x squared might have been the derivative of blank part that follows along. Now, the only way to end up with a cosine of blank would have been to have started with a sine of blank. And since the blank doesn't change, that would have been a sine of x cubed. Now, does this work? Well, let's see. We could check by simply taking the derivative and seeing what we'd get. Now, the derivative of this would be the cosine of blank times the derivative of blank, just like we said. The blank is x cubed. The derivative of x cubed is 3x squared. And so when we simplify that, that would come out to being 3x squared times the cosine of x cubed. And so we'd be off from the antiderivative we want by a factor of 3. But since constants come along for the ride, if we had thrown on an additional 1/3 in front of everything, then those 3's would have canceled, and we'd have gotten back exactly what we wanted to. So we've just concluded that an antiderivative of x squared cosine of x cubed dx is equal to 1/3 sine of x cubed plus an integration constant. And now that we have one of those integration constants, we can evaluate it from 0 to the cube root of pi in order to work out this definite integral. When we do that, we're going to have 1/3 times the sine of the cube root of pi cubed minus 1/3 times the sine of 0 cubed. I'm just ignoring that plus c this time around. So the sine of 0 is 0. This expression right here is just the sine of pi, and the sine of pi is 0. And so when all is said and done, we end up with a 0, which is a little anticlimactic. But the point of this problem wasn't that antiderivative. The point of this problem was getting a hold of an antiderivative of something complicated like this. Let's try another example. Let's say we want just to find an antiderivative of, x to the 4th times 3 plus x to the 5th to the 6th power dx. So how would we find an antiderivative for something like this? Once again, note that it's a product of two pieces. And since it's a product, we can't split the product up or integrate each one of the pieces separately, because that would violate one of our derivative rules. The only ways that we know how to see a product is the final result of a derivative, as an act of foiling it out, or by using a product rule or a chain rule. If this had been the act of factoring something, we could solve it by attempting to FOIL this expression out right here. But that's a sixth power, and that'd be a little bit too much work for me. A slightly different attack would be to assume that this piece right here came from the act of taking the chain rule on something. Now, if we ended up with a blank to the sixth power, and then junk, that must have been because we started out with something that looked like blank to the seventh power. Since the blank never changes, we'd have to have a 3 plus x to the 5 inside that expression. Let's see if this antiderivative would work. So we're going to go and take the derivative of this expression and see whether or not we recover x to the 4th times 3 plus x to the 5 to the 6th power. Now we're taking the derivative of blank to the 7th. According to the chain rule, that would be 7 blank to the 6th times the derivative of blank. The blank is 3 plus x to the 5. The derivative of 3 plus x to the 5 is 0 plus 5x to the 4th. Now if we collect and simplify our terms, we have 35x to the 4th times 3 plus x to the 5 to the 6th power. This is the expression that we wanted, but in the act of taking the chain rule, we've collected an extra constant in front, the scalar 35. So if we want to come up with a correct antiderivative, we're going to have to go and divide our original expression, our guess of 3 plus x to the 5 to the 7th power, and we're going to have to multiply that by 1/35. We're going to have to divide by a 35 to cancel with this 35 here. In the language of calc students, this number that's out in front is sometimes called the fudge factor. It's what we need to sort of fudge our initial guess in order to make sure that all the constants that come out of the chain rule are appropriately canceled. But now that we've found one antiderivative, we've found them all. We can conclude that the antiderivative of x to the 4th times 3 plus x to the 5 to the 6th is 1/35 times 3 plus x to the 5 to the 7th power, plus an integration constant to make sure that we cover everything. Now, this method of guessing and checking is actually a fairly effective tool, but we can systematize this approach a bit by a method called substitution. To motivate the method of substitution, let me remind you what the chain rule says. The chain rule says that if we have the derivative of one function stuffed inside of another function, f of g of x, then we take the derivative of the outer function, f prime, and then replace the inside with g of x, and follow it up with the derivative of that inside function. Right, that's the official formulation of the chain rule. So since the derivative of f of g of x is f prime of g times g prime of x, that's the same thing as saying that the antiderivative of f prime of g of x times g prime of x dx would be equal to f of g of x plus an integration constant. If we let capital F be the same thing as little f prime, then the expression on the left of this can be rewritten as the integral of capital F of g of x times g prime of x dx. But what about the right-hand side? Well, lowercase f is one of the antiderivatives of f prime, so the expression on the right is therefore one of the antiderivatives of capital F. And I'm going to use a temporary dummy variable just so that I can set the stage for the way we use this. So the formula on the right is one of the capital derivatives of capital F of x. But we're not plugging in x, we're plugging in the function g of x. And so we're taking this formula and replacing the variable with g of x. And so this formula right here, which is nothing more than the chain rule under a slight change of notation, is called the change of variable formula. And it instructs us on something called the method of substitution, which will allow us to go and work out antiderivatives involving the chain rule without having to do the guess and check that we saw in the previous two examples. The basic idea is summarized in the following steps, which will run side by side with an example. Let's revisit our example from before, the antiderivative of x squared sine of x cubed. The first step in the method of substitution is to choose a substitution. The idea here is you're trying to figure out what would have been the blank bit inside of the chain rule. And so usually what we do is we're going to go and choose something which is inside the parentheses in order to help us out with this process. So in our example to the right, we have this expression of x cubed in the parentheses. And so I'm going to go and let u equal x cubed. Next, we're going to take the derivative of that substitution, which would be the derivative of the blank part in the chain rule. So in this example, we're going to have du dx is equal to 3x squared. The third step is to rewrite this as a differential equation with a simplified right-hand side. What that usually means is it's going to be a two-step process. The first thing we're going to do is we're going to take and multiply both sides of this equation by dx. So we're going to have du is equal to 3x squared dx. And then, if we have any constant on the right-hand side, we're going to divide it. And so we're going to end up having 1/3 du is equal to x squared dx. This is sometimes called the differential for the substitution, as opposed to the actual substitution, which we made at the beginning. These two steps, these two equations right here, are going to form the heart of making a substitution. And in fact, the next step, step 4, is going to be the most important one. We have to fit the differential. What that means is we're going to have to go and see if we have the expression x squared dx in our integral. And if we do, we're going to replace that x squared dx with a 1/3 du. Now, let me bring back my integral down to here. This was the integral of x squared times cosine of x cubed dx, which for convenience I'm just going to rewrite as cosine of x cubed times x squared dx. So in fact, I do have an x squared dx. So this piece right here, I'm going to go and replace with 1/3 du. Now that I've got the differential fit, we're going to replace all of the remaining x's using our u. Remember that our u is x cubed, so every time we see an x cubed, we'll replace it with the letter u. And so our original equation, which was full of x's, can now be rewritten in the relatively simple form of 1/3 times the cosine of u du. And so we have a basic trig integral. If we antidifferentiate that, we would have 1/3 times the sine of u. And that's in fact what our general next step is to integrate what hopefully is the simpler u integral. Now our final answer is an antiderivative, but it's an antiderivative using the letter u, which wasn't a part of the original problem. So what we need to do at the very, very end is to simply back substitute, which means to go and replace the u we made up with the original value of x cubed. And so we come up with a 1/3 sine of x cubed plus c. And there's an antiderivative. Let's work out the general antiderivative of 4x cubed over x to the 4 plus 1 quantity squared dx. Now I'm going to start this problem out by prepping it. So I'll take care of those denominators. We have 4x cubed times x to the 4th plus 1 to the minus 2 dx. Now, when I look at this integral, I see that it's a product. And we've been talking about this. When we see products of integrals, we have to take it nice and slow. Now, the two most common attacks we've seen has been to expand the antiderivative in the hopes of using the sum and scaling rules, or to hope that it's something that we could use a chain rule on. Well, evidently I'm not going to be able to expand this out. We don't have an expansion formula for -2. 2's and 3's are about all we've got. And you can't distribute this in until you take care of that power. So this is pretty much algebraically inert to us. So could we try the method of substitution on it and undo the chain rule? Well, a substitution requires us making a choice of what we think the blanked expression would have been, so you hunt for expressions inside of a parenthesis. And so, u equals x to the fourth plus 1 would be a good candidate. The second step, we take the derivative of our substitution to have a 4x cubed. Now what we're going to do is we'll multiply both sides by a dx to end up with du is equal to 4x cubed dx, and divide both sides by 4, so 1/4 du is equal to x cubed dx. And so this substitution will work as long as we can find an x cubed dx in the original integral. Now, let me rearrange things around in this. We're going to have the integral of 4 times x to the fourth plus 1 to the minus 2 times x cubed dx. And that's the piece we're looking for. So this means the substitution will work. I can replace the x cubed dx with 1/4 du. And then any other x in the problem I can replace with the original substitution. So every x squared, or x to the fourth plus 1, can be replaced with a u. And so our substitution, our original integral, can be rewritten as the antiderivative of u to the minus 2 du. That's just a basic power function. So we up the power by 1 and divide by the new power. And so that simplifies to negative u to the negative 1. So we have an antiderivative in the variable u. Now we'll back substitute in order to come up with negative x fourth plus 1 to the negative 1. There's one antiderivative, and that would give us all of them. By way of checking our answer, let's just take the derivative. And one of the things we should note is that right off the bat, we're going to use the chain rule on this. The derivative of negative blank to the negative 1, well, the negative comes along for the ride. The derivative of negative blank to the the derivative of blank to the negative 1 is negative blank to the negative 2 times the derivative of the blank. The blank was x to the fourth plus 1. The derivative of that is 4x cubed. And so we end up with 4x cubed times x to the fourth plus 1 to the negative 2. And that's exactly our original integral. Let's try to find the general antiderivative of sine of the square root of x over the square root of x dx. So I'll start by prepping this to end up with sine of x to the 1/2 power times the bottom part, which is x to the negative 1/2 power dx. Once again, I see that this is a product, so my usual tricks have been to expand the product out, which I don't know how to do without inventing some kind of crazy new trig identity, or to attempt to use a substitution, which would be to undo the chain rule. Now notice that there's something in parentheses here, so there's at least a good candidate for a substitution, u equals x to the 1/2. So, once you've made your substitution, the next several steps are kind of mechanical. We'll take the derivative of our substitution to come up with 1/2 x to the negative 1/2, multiply both sides by the dx, and then I'm going to get rid of this constant in front, so I'll multiply both sides by 2 to end up with 2 du is equal to x to the minus 1/2 dx. This substitution will work as long as we have an x to the minus 1 dx in our integral. And in fact, in this case, it's the backside of the integral. So we can make the substitution. The x to the minus 1 dx I can replace with 2 du, and the x to the 1/2 I can replace with a u. And so under the substitution, we have sine of u times 2 du, the antiderivative of that. 2 comes along for the ride, and so this is really twice the antiderivative of the sine of u du. Now the antiderivative of sine, let's see, the antiderivative is cosine of u with a negative to counteract the negative from its derivative, and so that comes up with negative 2 times the cosine of u. If we back substitute, we get negative 2 times the cosine of x to the 1/2 power. There's one antiderivative, and adding on the plus c collects all of the antiderivatives. And again, by way of checking our work, let's take the derivative of negative 2 times the cosine of x to the 1/2 power. So the derivative of negative 2 times the cosine of blank, well, negative 2 comes along for the ride. The derivative of cosine of blank is negative sine of blank times the derivative of blank. The blank is x to the 1/2 power. The derivative is 1/2 x to the negative 1/2. So these constants cancel, and if I bring that up to the front, we have x to the negative 1/2 times the sine of x to the 1/2 power. And that's exactly the original integral. Let's try another example. The antiderivative of x squared times x to the 5 plus 1 quantity squared dx. Notice that this integral has already been prepped. There's no square roots or denominators or radicals in it. It's also a product, just like the other ones have been. So we could attempt to try a substitution on this example. We have something in parentheses, u being x to the 5 plus 1. So let's go through the process of trying a substitution. We take the derivative of this expression, du dx, to come up with 5x to the 4th. We can multiply both sides by dx, and then divide both sides by 5 to simplify the right-hand side, and end up with 1/5 du is equal to x to the 4th dx. So as long as our integrand has an x to the 4th dx in it, we can make the substitution work. Now if I rewrite my integrand, just so I can see it a little bit more clearly, we've got x to the 5 plus 1 squared times x squared dx. And that would suggest that we don't have quite enough to make this thing work. We've got, well, an x and an x and a dx, and we need an xx and a dx in order to pull the substitution off. Said differently, this substitution doesn't fit. There's not enough x's needed to make the differential part happy. Now you might say, why don't we just divide both sides by an x squared? So I have 1 over 5x squared du is equal to x squared dx, because then I have exactly that. So if I go and I make the replacement, I'm going to have the integral of, well, let's see, the x squared dx could be replaced with 1 over 5x squared du, and then every single one of my remaining x's in the integral could be replaced with a u, so this becomes u to the 2. And so now we have the integral of 1 over 5x squared times u squared du. The only problem with this is that this integral now has two different letters running around in it, two different variables. This x is not a constant, so you can't pull it out of the integral like you could with the 1/5. It's connected to the u squared by this equation up at the top. So you're now attempting to find an antiderivative of a function of two variables where the two letters are somehow connected. Now the subject that allows you to understand how to integrate a function that has two interconnected variables is Calc 3, and that's not where we are right now. So for us, if we ever see an integral that has two different variables, neither of which are a constant and they're connected to each other, we should instead think that two variables equals nonsense, that this integral right here is simply ill-defined. So our original substitution of x to the 5 plus 1 doesn't work. So what should we do? Well, you might have noticed on the two previous examples, I asked if we could expand the expression out first, and I deliberately decided not to do that this time around. But this one, with the power of 2, could in fact be FOILed out. We could expand the expression in parentheses first. X to the 5 squared is x to the 10, plus 2 times this, or 2x to the 5, plus the final term squared, which is 1, dx. And now that the power is off, we can distribute the x squared in order to obtain x to the 12, plus 2 times x to the 5 plus 2, or x to the 7, plus x squared dx. And then each one of these individual pieces can be integrated according to the sum and scaling rules. So the antiderivative of x to the 12 is 1/13 x to the 13th. The 2 comes along for the ride. The antiderivative of x to the 7 is 1/8 x to the 8. And the antiderivative of x squared is 1/3 x cubed. So here's one antiderivative. If I clean it up to get 1/13 x to the 13th, plus 1/4 x to the 8th, plus 1/3 x cubed, plus an integration constant, and we have every possible antiderivative. So sometimes we want to use a substitution. Sometimes we just want to FOIL things out. This might be a time to give a good rule of thumb for when we want to use these two techniques. When should you use a substitution? I can give two basic guidelines. The first guideline, ask yourself, would the derivative involve the chain rule? If you came across an expression like x squared times the cosine of x cubed, if instead of having to anti-differentiate it, you had to differentiate it, would you at some point need to use the chain rule? If so, then it's probably a good candidate for substitution. But I can follow that up with the second good rule of thumb. Can you expand it out? Can you go and take the expression that you're looking at and actually go and FOIL the thing out? If you can expand it out, you can turn a giant product into a bunch of smaller pieces, and maybe none of those would require a substitution. Now, once again, the best way to do this is to practice, so let's take a look at a couple more examples. Find the general antiderivative of 1 over theta squared times the secant 1 over theta tangent 1 over theta. So the first thing I'm going to do is I'm going to prep this. This becomes the integral of theta to the negative 2 times the secant of theta to the negative 1 times the tangent of theta to the negative 1 d theta. So if I take a look at this expression, the first thing I notice is that it's a product. And if I were to take the derivative of this, I would definitely use the chain rule in two different spots. Moreover, it's a product, and I have no idea how to expand this thing out by using a rule of algebra, so that would seem like it meets both criteria for being a good substitution problem. It has a chain rule derivative, and I can't FOIL the thing out. So let's try a substitution. What substitution should I pick? Well, I have an expression in parentheses in two different spots, so let's try letting u be that expression in parentheses. Now I'm going to take the derivative, du d theta, and come up with negative theta to the negative 2. Now we're going to go and multiply both sides by d theta, and divide both sides by negative 1, to end up with the differential equation, negative du is equal to theta to the negative 2 d theta. And the question becomes, is that a part of our original integral? Well, in this case, it would be the bookends. The theta to the negative 2 times d theta are the two extreme ends of this integral, and so I can replace theta to the negative 2 d theta with negative du, and so I'm going to have a negative du at the back end. Now I can go and replace every other instance of theta to the negative 1 with u, which means I'm going to have secant of u times the tangent of u. So I pull that negative 1 out to the front, and we're anti-differentiating secant u tangent u du. Now, this is another product that I can't expand out, but fortunately, this should be one of the derivatives we recognize. That's exactly the derivative of the secant function. So we have negative the secant of u. And now that I've got an antiderivative, I can back substitute to end up with secant negative of theta to the negative 1. There's one antiderivative, and this gives me all of them. And so, once again, we have an antiderivative. While we're playing with trig, let's take a look at another example, the antiderivative of the quantity sin x plus cos x squared dx. So the first thing I'm going to do is prep this. This is the antiderivative of the sine of x plus the cosine of x squared dx. Now, if I were going to go and take the derivative of this expression, I would certainly use the chain rule because I have something squared. But I can FOIL this thing out. And so my rules of thumb would say that since it's possible to FOIL this expression out, I might as well do that. So if we expand this out, we're going to have, let's see, the first term squared, sine of x quantity squared, plus 2 times the first term times the second term, 2 sine of x cosine of x, plus the last term squared, that's the cosine of x quantity squared dx. So we've expanded this thing out into what amounts to being 3 smaller integrals. Even better, notice that if I rearrange the terms a little bit, we get sine of x quantity squared plus cosine of x quantity squared plus 2 times the sine of x times the cosine of x dx. And this expression, cosine squared plus sine squared, if it's the one trig identity you can't forget, it's this one. This is always equal to 1 by the Pythagorean identity. And so this simplifies to 1 plus 2 times the sine of x times the cosine of x dx. We can now split this integral up into two pieces using the sum and scaling rules into the integral of 1 dx and then twice the integral of sine of x cosine of x dx. Now the integral of 1 is just x. So we have x plus 2 times the antiderivative of the sine of x times the cosine of x dx. But now I have to work on this integral right here. Now notice once again that it's a product, so I can't split the integral up into two pieces. The derivative of something like this wouldn't involve the chain rule, but it is a product that I don't have an immediate FOIL formula for. So this might be a substitution problem, because it looks, at least initially, as though it's unfoilable. So we could try a substitution on just this piece. So let's give ourselves some room and see what that might be. So, what should I try? Well, I have an x in parentheses, so I could try letting u be x. If we take the derivative of that, we get du dx is equal to 1. So if I multiply both sides by dx, I get du is equal to dx. And evidently every integral has a dx in it, so we could make that substitution. We could go and replace the dx with du, and then replace every single x with u, and we would end up with the sine of u times the cosine of u du. And congratulations, we have exactly the same antiderivative that we had before, but we've just converted all of the letters from u to x. This is kind of an object lesson right here, is that this substitution never works. You can always make it, but the substitution u equals x doesn't do anything interesting. So let's try a slightly different substitution. We're kind of flying blind, but maybe we could try letting u be one of the two pieces of the integral. So we could try letting u be, say, the sine of x. Then if I take the derivative, du dx is equal to the cosine of x. And if I multiply through by a dx, we end up with cosine of x dx. And so this becomes my new differential equation for the integral. And what do you know? We have a cosine of x dx, so this substitution will work. In other words, the integral of sine of x times cosine of x dx, we can replace the cosine of x dx with just du, and now we can replace every instance of sine of x with the original substitution u, and we have the antiderivative of u du. That's just a basic power function. It integrates to 1/2 u squared. And if we back substitute, we end up with 1/2 times the sine of x quantity squared. And so now we have an antiderivative for this piece. So if we pick up where we left off, we have x plus 2 times the antiderivative we found was 1/2 the sine of x squared. So these terms cancel, and we're left with x plus the sine of x quantity squared. That's one antiderivative, and then adding a c gets me all of the other ones. But wait a second. We made the substitution by, at random, letting u be one of these two pieces. What would have happened if we'd let it be the other piece? Say u being cosine of x. Well, if I take the derivative, du dx, that would have been negative sine of x dx. Sorry, negative sine of x. If I multiply both sides by dx and divide both sides by -1, we'd end up with negative du is equal to the sine of x dx. And if you look, we do have that sine of x dx has been formed as the bookends of the integral. So we could replace these two pieces with negative du. And then every instance of cosine of x would become a new u. And so our integral would have become u times negative du, or negative the integral of u du. Again, that's a power function. It antidifferentiates to 1/2 u to the square. And if we back substitute, that would have been negative 1/2 times the cosine of x quantity squared as an alternate answer to the antiderivative of cosine of x dx, and that would have led to a completely different solution. An antiderivative of x plus 2 times negative 1/2 the cosine of x quantity squared, or x minus cosine of x quantity squared plus c. So which of these two answers is right? Is it possible to have two completely different substitutions who get me valid answers? Well, yeah. I mean, there's nothing wrong about the individual steps, and in fact, I can show that these two answers are both reasonable. For if we remember the Pythagorean identity, which we've already seen once so far, sine of x squared plus cosine of x squared equals 1, then it follows, for example, that the sine of x quantity squared is equal to 1 minus the cosine of x quantity squared. And so, in particular, our antiderivative on the left of x plus the sine of x quantity squared is the same thing as x plus 1 minus the cosine of x quantity squared. Said differently, that's x minus the cosine of x quantity squared plus 1. And that's entirely the role of the plus constant. There's no such thing as the one antiderivative, but any two antiderivatives can only differ by a value that's a constant. Let's take a look at another example. X to the 5 times the square root of x cubed plus 2 dx. Now if we go and we prep this, we're going to have the integral of x to the 5 times x cubed plus 2 to the 1/2 power dx. Now looking at this integral, I notice that it's a product, which means I'm going to have to do a little bit of thinking on something like this. Now my thinking, I can't expand this out because of that fractional power, which means I also can't distribute this in because I have to take care of the power. Moreover, if I was going to take the derivative of this expression, I would have to use the chain rule to handle this blank to the 1/2 expression. Put those two things together, and it says that this is a great candidate for u substitution. The u that I'd like to work with is x cubed plus 2, because that's one of the expressions in parentheses. We take the derivative of that, we get du dx is equal to 3x squared. So I multiply both sides by dx and divide both sides by 3 in order to simplify the right-hand side, and also, if you've been catching along, to collect the fudge factor. And we end up with a 1/3 du is equal to x squared dx. So, do we have an x squared dx? Well, let me rewrite this integral real fast. We have 1/3, or x cubed, plus 2 to the 1/2 power times x to the 5 dx. We're looking for an x squared dx. Turns out on this one we have an x to the 5 dx. So does this differential fit? Now you might remember we did an example that was sort of similar to this a few iterations ago, but there's one fundamental difference this time round. To make this differential work, we essentially need an x and an x and a dx. But in this integral, we happen to have an x and an x and an x and an x and an x dx. In some sense, we have more x's than we need, rather than fewer. So this actually does fit. And if I rewrite the integral just a bit, I can make that much more patently obvious. X to the 5 is x cubed times x squared. And written like this, I see that we do indeed have an x squared dx. So I can replace the x squared dx with, well, what does our differential say? 1/3 du. And so this can now be replaced with 1/3 du. Now, we built the substitution to handle the x cubed plus 2. So this x cubed plus 2 can now be written as u to the 1/2 power. But something different has happened this time around. We have this extra x cubed, what's known in the language of these problems as a leftover. We have an expression in x that the substitution wasn't built to handle. Well, at first you might think we're sort of stranded, that there's nothing that we can do, but we're actually completely in control in this problem. All we have to do is go back to our original substitution. Our original substitution, which was u equals x cubed plus 2, is the same thing as saying that u minus 2 is equal to x cubed. right? Our rule for substitution says we go back to the original equation to handle any of the x's. And so if I ever see an x cubed, I can now replace it with a u minus 2. And so our substitution becomes u squared to the 1/2 power times u minus 2 times 1/3 du, or 1/3 u to the 1/2 power times u minus 2 du. So this substitution hasn't been as simple as our other ones. So now what do we do with something like this? We have this brand new integration problem. And if I look at it, what do I see? Well, I see that it's a product. So what's my thinking for a product? Well, can I expand it out? Sure. Looks like this one is perfectly expandable. So if I expand it out, we're going to have 1/3 times u to the 1/2 times u, that would be u to the 3/2 power. Distributing across the second piece, we'll have a negative 2/3 times u to the 1/2 power du. These are now just two power functions, so we can integrate them one at a time. The 1/3 comes along for the ride. To anti-differentiate u to the 3/2, let's see, we up the power by 1, u to the 5/2, and then I have to multiply by 2/5 as a fudge factor. Take away 2/3 comes along for the ride. The antiderivative of u to the 1/2, well, we up the power by 1, so we're going to have u to the 3/2, and then we have to divide by, or multiply by 2/3 to get our fudge factor. And so if we clean this up, well, let's get some more room so I can put this all on one page. And I'll continue this work right up here. We end up with 2/15 times u to the 5/2 minus 4/9 times u to the 3/2. If I back substitute, that's 2/15 times u, which was x cubed plus 2 to the 5/2 power, minus 4/9 times x cubed plus 2 to the 3/2. So there's one antiderivative, and adding a c gets me all of them. So once again, this is a technique called substitution with leftovers, and you might be asking, was that really legit? Perhaps the easiest way to check would be, well, to simply take the derivative. So if we take the derivative of 2/15 times x cubed plus 2 to the 5/2 power minus 4/9 times x cubed plus 2 to the 3/2 power, well, let's see, the 2/5 would come along for the ride, 2/15. The derivative of blank to the 5/2 power would be 5/2 times blank to the 3/2 power times the derivative of blank. The blank is x cubed plus 2. The derivative of that is 3x squared. Minus, the 4/9 comes along for the ride. The derivative of blank to the 3/2 power would be 3/2 blank to the 1/2 power times the derivative of blank. The blank again is x cubed plus 2. The derivative of that is 3x squared. So if we simplify this, well, let's see, the 2's cancel. The 3 and the 5 go into the 15, so we're just left with x squared times x cubed plus 2 to the 3/2 power. Over here, let's see, the 3 and the 3 go into the 9. The 2 goes into the 4 twice, leaving me with a 2x squared times x cubed plus 2 to the 1/2 power. Now, that's not exactly what we had up here, but I might be able to simplify that by factoring. And if I notice, there's an x squared common to both pieces, and there's also an x cubed plus 2 to the 1/2 power. So if I pull those two pieces out, the x squared and the x cubed plus 2 to the 1/2 power, then what we'll have left over, well, let's see, we've lost this, and we've pulled a 1/2 power out. 3/2 minus 1/2 is 1, so that's an x cubed plus 2. Over here we factored out the x squared and all of these, so that's going to leave me with a negative 2. So these two expressions cancel, and we have x squared times x cubed plus 2 to the 1/2 power times an x cubed, which gives us a grand total of x to the 5 times x cubed plus 2 to the 1/2 power. And that's a perfect match. So once again, we've seen that our basic techniques for handling products, which are to expand things out or to use a substitution, are in some sense predicting whether or not we're going to go and use the chain rule, which is what substitutions handle, or whether or not we're going to go and factor something out in the last step, which is what foiling out an integrand does. Let's try a definite integration problem. The definite integral from 0 to 1 of x times x squared plus 2 quantity squared dx. Now, according to the fundamental theorem of calculus, we need to dig up an antiderivative of x times x squared plus 2 squared dx, and then we can evaluate that from 0 to 1. Now, looking at this again, I see that we have a product. When we're dealing with products, it seems as though our common options are to expand the thing out or to try a substitution. And in this case, since I can expand it out, I'm going to give that a shot first. My experience has been that expanding works better than substitutions if I can do that. So we'll FOIL out the inside, x squared squared, plus 2 times x squared times 2, plus 2 squared, which will then evaluate from 0 to 1. I can distribute that x in, so that's going to get me the antiderivative of x to the 5 plus 4x cubed plus 4x dx, evaluated from 0 to 1. Now we can antidifferentiate each one of these pieces individually. We're going to get a 1/5, we're going to get a 1/6 x to the 6th. The antiderivative of 4x cubed is exactly x to the 4th. The antiderivative of 4x squared will be 4 times 1/2 x squared, evaluated from 0 to 1. And that 4 times x squared, we can just simplify that to 2. Now if I plug in 1, we're going to end up with 1/6 plus 1 plus 2. If we plug in 0, we're going to end up with 0 plus 0 plus 0. And then we'll subtract the two results. And so that's going to leave me with a grand total of 3 1/6, or if you'd like, 19/6. So what's the whole point of this example? Well, the whole point of this example is to try this a second way. Let's try this with a substitution. Because this is a good candidate for a substitution, if I were to differentiate this, I would in fact have to use the chain rule at one point. That would also suggest that the blanked expression would be x squared plus 2, so let's set that for my u. So we take the derivative du dx, and that comes out to being 2x. I'll multiply both sides by du, or dx, divide both sides by 2, and end up with 1/2 du is equal to x dx, the differential we need to fit to make the substitution work. Will the substitution work? Well, let's take a look at what we've got here. We had the integral of x times x squared plus 2 squared dx. And if we look at that, the x dx are the bookends. So the x dx can be replaced with a 1/2 du. The substitution was built to handle every instance of x squared plus 2, so we're going to have a u squared. And so the antiderivative becomes 1/2 u squared du. Once again, we've got a power function. The 1/2 comes along for the ride. The antiderivative of u squared is 1/3 u cubed, which gives us 1/6 u cubed. If we back substitute, that's going to get us 1/6 times x squared plus 2 to the 3rd power. That's one of our antiderivatives. Now, since we're doing a definite integral, rather than add the plus c, I'll simply evaluate that from 0 to 1. So if I plug in 1, we're going to have 1/6 times 1 plus 2 cubed. If we plug in 0, we're going to have 1/6 times 2 cubed. So if we simplify that, 3 cubed is 27, so this is 27/6. 2 cubed is 8, so that becomes 8/6, and 27 take away 8 is exactly 19/6. And so the answer checks out. We could do this with expanding, we could do this with a substitution. Now, what's the only reason I'm bringing this up? Substitution is a technique that's designed to find antiderivatives. If you're careless with it, you can be led down the wrong path. The most common mistake people make when they're using when they're using substitution with a definite integral is to assume that the limits don't change. The original problem was the integral from 0 to 1. So shouldn't the u limit be the integral from 0 to 1 as well? Well, look what happens if we keep those 0, 1 on at each one of these steps. So our last step would have been 1/6 u cubed from 0 to 1. If we plug in 1, that would have been 1/6. If we plugged in 0, that would have been 0. And we would have ended up with 1/6, which is clearly the wrong answer. So keep this in mind. U substitution is a technique for finding antiderivatives. In its current incarnation, it cannot be used with limits. If you forget and you actually plug the limits into the u integral, you will get the wrong value. That being said, it is possible to modify the u substitution technique to handle limits. The basic idea goes like this. Suppose you really want to keep these limits intact. You don't want to actually make the substitution, the back substitution in the last step. You would actually like to be able to plug in limits at this step. But it can't be the limits 0 to 1. So what do you need to do? Well, you're going to go back to your original substitution. The original limits in the problem were x equals 0 and x equals 1. But the first step of your substitution is to give you away from converting from the letter x to the letter u. So if x is ever equal to 0, then u is going to be 0 squared plus 2, which is 2. Similarly, whenever x is equal to 1, u will be 1 squared plus 2, or 3. So whereas the original integrals went from 0 to 1, it makes sense that the u integral should go from u equals 2 to u equals 3. So we can change not only the integrand, the x's and the dx's into u's and du's, but we can change the original limits, which were x going from 0 to x going from 1, into u limits, u going from 2 to u going to 3. If we were to follow along, we would have a 2 and a 3 at each one of these steps. And so at the very, very last step, we would be plugging in 3 and plugging in 2. If we do that, we're going to have 1/6 times 3 cubed minus 1/6 times 2 cubed. That gets me 27/6, take away 8/6, which is, once again, 19/6. And this time we recover the correct value. Me personally, I'm a bigger fan of the antiderivative method for 2 reasons. Reason number 1 is actually seeing the antiderivative gets me something to check. And reason number 2, you might have noticed that when I do substitutions, I change the color of the ink so that I know I'm in a substitution. So in my particular methodology, when I have to substitute, or when I plug into the very, very last step, I'm in the wrong color chalk. To me, that's just an aesthetic difference. There are some places where this changing the limits in the middle of the substitution is actually a very, very useful time saver. So you can pick between the 2 methods. In fact, let's just illustrate it with one final example. Let's take a look at the definite integral of the square root of 1 plus the cube root of v all over the cube root of v quantity squared dv, which is a little horrifying looking. So let's start by doing what we always do. Let's prep it first. This becomes the integral from 1 to 4. The numerator is 1 plus the cube root of v to the 1/3, to the 1/2 power. The denominator can be written as v to the negative, because it's in the denominator, 2/3 power, because it's a cube root squared, dv. Now when I look at this expression right here, the first thing I notice is that it's a product, so I'm not allowed to go and split it up. I also note that I can't FOIL it out because of that 1/2 power here, which means I'm not allowed to expand it. The next thing I notice, though, is that if I were to take the derivative of it, I would have to use the chain rule on this piece right here. So all of those things together suggest that this is an excellent candidate for a substitution. What would I want to pick for my substitution? Well, let's let u be the thing in parentheses, 1 plus v to the 1/3 power. If we take the derivative, du dv, we're going to end up with 1/3 v to the negative 2/3 power. I'll multiply both sides by a dv, and also multiply both sides by a 3 to simplify that right-hand side, and we're going to have 3 du is equal to v to the negative 2/3 dv. And check it out. We have a perfect match for our differential. So we can replace this with the expression 3 du. Our substitution was built for 1 plus v to the 1/3, so that's just going to become u to the 1/2 power. And our limits? I'm simply going to go and ignore them entirely. I'm looking for an antiderivative. So if I look for just an antiderivative, this can be simplified to 3 times the antiderivative of u to the 1/2 power du. So if we integrate that, we're going to have u to the 3/2 power. We'll multiply that by a 2/3 power, And so that's going to simplify to u to the 3/2 power. If we back substitute, that becomes 2 times u, which is 1 plus v to the 1/3 power, raised to the 3/2 power. Now normally I'd stick on a plus c, but in this case I had limits, but instead I'm going to evaluate this from 1 to 4. So if I plug in 4, I'm going to have 2 times 1 plus 4 to the 1/3 power to the power of 3/2. If I plug in 1, I'm going to have 2 times 1 plus 1 to the 1/3 power to the 3/2. And so let's see, if we simplify that, that's going to be 2 times 1 plus the cube root of 4 to the 3/2 power, minus 2 times, well, let's see, that's just going to be 2. And so we're going to have, well, the square root of 2 cubed. That's not particularly pretty, but that's the numeric value of our antiderivative. Now, what would be the alternate method of getting to this? You could, if you wanted to, change the limit in transit. So rather than actually making the back substitution like I did here, we could actually change the limits on the integral during the substitution. We take the two original limits, which were x equals 1 and x equals 4, and replace them into their corresponding u values. If I plug in 1, I'm going to have u is equal to 1 plus the cube root of 1, which is 2. And I'll have the second value, 1 plus the cube root of 4. And so our original limits of 1 to 4 become the new limits of 2 to 1 plus the cube root of 4. And so those limits come along for the ride. And so our final evaluation would go from 2 to 1 plus the cube root of 4. And so if we plug in directly, we'll have 2 times 1 plus the cube root of 4 to the 3/2 power. Take away 2 times 2 to the 3/2 power. And that matches what we get. 6 of one, half a dozen of the other.